Hello, everybody. Thank you for joining us today for the ninth edition of the Ask an Expert webinar series entitled Engineering Canada's Offshore Wind Future. My name is Claire Kleinknecht. I'm the policy analyst with Marine Renewables Canada, and I'm going to be the host for today. For folks that might be new to our organization or webinar series, Marine Renewables Canada is the National Association for Offshore Wind, Tidal, Wave, and River Current Energy, and we've been hosting this webinar series over the past few years to try and tackle Canadians' greatest questions about offshore wind. Before we get started, I want to take a moment to recognize and acknowledge the traditional territories and Indigenous peoples of the different lands we are all on today. I'm hosting this webinar from Mi'kmaq, the ancestral and unceded territory of the Mi'kmaq people. Given that we're coming together to discuss offshore wind, I also invite us all to think about the impacts that marine renewable energy projects might have on Indigenous communities and how we can improve our own understanding of local Indigenous peoples and their cultures to ensure that projects move forward inclusively and respectfully. So before turning it over to our guest today, a few housekeeping notes. We will be recording this webinar and it'll be uploaded to MRC's website and YouTube page. The bulk of today's webinar will be a presentation followed by a short period for questions. And the presentations will come from our two presenters we have here today. I'll also just quickly remind folks that questions can be asked at any time during the presentations in the Q&A tab at the bottom of your screen. And I'll just plug as well that Marine Renewables Canada has opened our call for abstracts for the technical track as well as proposals for the member workshop. And these are open until May 15th. Additionally, we have an upcoming event here in Halifax on May 12th, a spring summit focused on supply chain. So with that, I would like to introduce our two guest speakers, Blair McDougall and Walid Alatawi. Blair is the founder and president of Waterford Energy Services and co-founder of Technical Energy Solutions with nearly 30 years of experience across offshore renewables, hydrogen, and oil and gas. He has led complex global projects in areas like offshore wind, subsea cable operations, and port infrastructure, and brings expertise in engineering, operations, and project delivery. Walid is the managing director and director at Offshore at JBO Engineering Group with over a decade of experience himself in offshore wind. He specializes in the design and optimization of offshore foundations, towers, and structural systems, delivering reliable solutions for offshore wind projects. So today they're going to be joining us to provide an overview of the engineering behind offshore wind development, from site data and seabed conditions to foundations, cables, and grid connection. Together, they're going to share their practical insights and lessons learned from projects around the world and what this can mean for Canada's offshore wind future. So thank you both for joining me, and I'll hand it over to you.
All right, thanks a lot, Claire. Do you hear me okay?
Yep.
All good. And can you see my screen?
Yep. Looks great.
Great. All right. Well, thanks a lot for the introductions and good morning or good afternoon, wherever you may be from beautiful sunny Halifax on a lovely April spring day. So as Claire said, I'm Blair McDougall, and I'm going to start us off here. So a little bit on the agenda, really quick. So we went through the introductions. We're going to speak about wind, wave, and site characterization for the area, the state of the art for foundation for fixed bottom offshore wind, pre-feed considerations for monopile or jacket design, onshore grid integration, export cable route and landfall topics, feasibility of fixed bottom offshore wind in Nova Scotia, the samples of regulatory advisory roles in Europe and Asia and the US for JBO. And then a wrap-up discussion. We'll talk about risks and try to bring things to a conclusion, and then leave hopefully 15 minutes or so for Q&A. I will not get into really any great detail on a few topics. I think it's worth mentioning. I'm not going to get into a detailed discussion on Wind West, for example. It'll be very light touch on ports and infrastructure. And export power to X of molecules of hydrogen, of ammonia and things like that. We will not get into that type of a discussion either. All right, a little bit of background about Waterford Energy Services, or WESI as we sometimes call it. We've been working for major energy clients in Canada, the US, the Mediterranean, Europe, South America, Africa, and Asia. Most of our history has been offshore oil and gas, but the last 5 or so years, we've been doing more and more work in the offshore wind space and renewable sector, driven mostly by two factors. One being the emergence of the US offshore wind market and the projects that are there. Been fortunate enough to do quite a bit of work on some of those projects. And then the emergence also obviously of the Canadian market, which is a few years behind the US, but nevertheless has hopefully a bright future ahead. A little bit about the JBO and Westy partnership. We signed an MOU between our companies in April of 2023 in Copenhagen, and that work continues to this day. Our collective mandate is to bring our local know-how and knowledge in the Canadian market to the expertise that JBO has specifically in offshore wind and foundation design and installation. So it's good to be speaking with Wally today to you all. Our projects globally are all over from Southern and Western Africa to the Mediterranean to Canada, the US, and South America. We have Canadians working all over the world today. Most of that work is in oil and gas. However, we do have people working, for example, in some of the offshore wind projects at this moment in the northeastern US. I feel it's important for myself, our organization, as well as a lot of my colleagues and probably most of you on this call. Canada has the benefit of a very vibrant offshore oil and gas industry, and the skills and experience and know-how we've gained over 60 years of exploration activity, 30 years of production activity, 2 FPSOs, 3 gravity-based structures, numerous subsea pipelines, subsea manifolds, 7 platforms, helps us be positioned well to talk about topics like this, that being offshore wind. A couple of snapshots of projects we've been involved in recently with both Boskalis and Ørsted. I'm going to go through this quickly because this is not really the content of our discussion, but shows some of the offshore wind experience that we've gained over the last several years through use of ports and infrastructure in our region, and things like inspection of equipment when it arrives in Canada for eventual deployment into the northeastern US. That could be work on structures such as transition pieces and monopiles, but also things like this offshore substation, which was located here in Atlantic Canada for almost a year before being installed off of Rhode Island. We've inked a collective white paper with JBO, which was released some time ago, is out for public consumption at the moment. And now I'm going to get into wind, wave, and icing conditions that are, let's say, unique for our area. All right, so if you can see this image, there's a number of sites in Atlantic Canada that have good data with respect to mid-ocean conditions, wind and wave. You can see the numbers on the left-hand side of the map. And on the right-hand side of the map, you would see corresponding numbers showing the annual mean wind speed along the bottom axis and annual significant wave height, mean significant wave height on the vertical axis. So if you see number 17 there, that is an area known as the Orphan Basin. It is not going to be subject to any offshore wind lease sales as we see it defined today. However, it shows that is the extreme from a wind and wave perspective when you look at the data in Atlantic Canada. So that's number 17. And bring your attention now more closer to Cape Breton and mainland Nova Scotia. See the numbers 10 and 11. And numbers 10 and 11 are sort of in the center part where all of the numbers are gathered together, showing annual wind speeds of Again, mean wind speeds, not maximums, of around 8 to 9 meters per second. Of course, there's definitely peaks and maximums that are above that number. And then the annual mean significant wave heights of around 2.5 meters. And again, that's a highly averaged and smooth number. The maximums would be much greater. But it helps to start putting a picture of the type of data that starts to then lead to the design. The design leads to cost, and the cost then leads to determining what LCOE may be for our region. So the purpose of this slide is to try and help people with some context. So what we've done is talking about wind only on this slide. You can see in the chart on the left, we've got a comparison of Massachusetts and the Vineyard Wind site and Nova Scotia in general, in particular the Sable Island Bank. So we figured that putting it in this context would help people to try and draw a comparison, because obviously Vineyard Wind is operational now off the state of Massachusetts. And if you can see differences in wind conditions and wave conditions and whatnot, that'll help you, draw some conclusions onto the viability of offshore wind in Atlantic Canada and Nova Scotia in particular. So if you look at mean wind speed, you've got measurements of between 8.5 to 9.2. That should be meters per second for Vineyard Wind. In Nova Scotia, again, mean wind speed by comparison would be slightly higher, 9.5 to 11.5. The wind consistency or seasonality is considered, strong in the winter, moderate in the summer on the Vineyard Wind site. However, very strong in the winter, and still strong in the summer, and a lot of variability as well due to the storms that come and go through our region. And I'll show a graphic on particular to hurricanes and storms for our region here in a couple of slides. Extreme wind, 50-year gusts between 40 and 45 meters per second. In Nova Scotia, again, around the Sable Island Bank, we're looking at between 45 to 55 plus meters per second. And those gusts are really driven by the North Atlantic storms that we see in the late summer and through the fall and winter season. And then finally, from an icing perspective, so I'm not talking about sea ice, I'm talking about things like freezing spray and icing of components that are above the water level, let's say. So it could impact things like helicopter transportation. It could impact icing on blades and components that are part of the nacelle, for example, and things like that. So to wrap up a wind consideration and icing, you've got Massachusetts and the Vineyard Wind site, tightly distributed wind speeds with a lower variance. The IEC class of wind turbine used there is a class 1/T, with General Electric providing the turbines in that project. And that is important because potentially in Nova Scotia, you would require a different class, a higher class, a more expensive class of turbine to withstand the environment in our area. So in Nova Scotia, from a wind perspective, you've got higher mean wind speeds, more extreme winds, more variability, and potentially higher costs due to these, additional wind considerations. So wind is good if you're building a wind farm, but it also needs to be considered within the design of the components, which can increase costs. Similarly, for wave considerations, I'll spend most of my time on the right-hand side, the table there. Mean significant wave height, 1.5 to 2.5 meters. 2.4 to 3.3 for Nova Scotia. The seasonal peak, significant wave height in the wintertime, 3 to 5 meters, 3.3 to 4+ meters, Nova Scotia. Typical summer significant wave height, 1 to 2 meters in Massachusetts Vineyard Wind Site, 1.5 or so around the Sable Island Bank. The extreme significant wave height of 8 to 12 on the Vineyard Wind Site, 10 to 12 at the Nova Scotia site. The extreme significant wave height, 12 to 13 for Vineyard, however, quite a bit higher, 13 to 15 plus at the Nova Scotia site. And then observed or modeled significant wave height maximum at the Vineyard Wind Site, 13 to 15 meters, and upwards of over 16 meters of significant wave height at the Nova Scotia site, driven mostly to North Atlantic storms. So again, this drives the design, which drives cost, which drives LCOE. With respect to atmospheric icing and freezing spray, that's more of a factor, more of a consideration in the Nova Scotia region. So sea temperature in the Massachusetts Vineyard Wind Site, more influenced by the warmer Gulf Stream influence. We still have that Gulf Stream influence off of Nova Scotia. However, we have also the added influence of the Labrador Current. Freezing spray, fairly rare, not absent, but fairly rare at the Vineyard Wind Site, but quite frequent in winter storms off of Nova Scotia. Atmospheric icing, minimal at the Vineyard Wind Site, but moderate to severe risk, Nova Scotia. And icing classification on wind turbine components, not necessarily required at the Vineyard Wind Site, however, may be required at a future Nova Scotia site, which would add cost onto a project in Nova Scotia, which may not be required at a Massachusetts or northeastern US location. This graphic shows hurricane tracks. This is from NOAA in the US, a public database, and this shows hurricane tracks over the last 10 years of category 1 through 5. On the left-hand side, you can kind of see some icons representing locations of current offshore wind projects off of Massachusetts. That would be the Vineyard Wind location, more or less. And then to the right, you see the turbine icons would be just to the north and east of Sable Island. I don't think you can see Sable Island very well on that map. But I think you can draw your own conclusions. You can see that these storms skirt sites like Vineyard Wind. They certainly influence or have somewhat of an influence on the Vineyard Wind Site as an example, but go directly over places like Sable Bank or French Bank, Sydney Bight, for example, on the Nova Scotia side. So that I thought that is a good visual to try and see how these storms can impact design, which impact cost and LCOE for our region. Couple more slides before I hand it over to you, Waleed. A little bit on geotechnical, geophysical, and ground conditions related to foundations and cables in our region. So we performed a geotechnical assessment in-house, trying to screen offshore Nova Scotia for suitability for use of monopiles as foundations. So we obviously didn't look at any floating regions, but we made a determination that in a lot of locations the conditions are quite favorable for monopiles and installation large percentage of sands in public available borehole uh, information that we reviewed. However, hazards do exist. So some of those hazards may be large boulders, for example. Um, they could be shifting sand dunes only on within the seabed, for example. Um, and so it's important, and I think past MRC workshops and perhaps webinars have looked at the importance of the currently available seabed and geotechnical data that is available, and the need for future data gathering campaigns. So some example of hazards on the seabed that we would need to be aware of on the left-hand side here. So, mapping the seafloor for boulders and sand beds using technologies such as side scan sonar, multi-beam data, giving accurate dimensions and locations of hazards such as boulders. Also using 2D or 3D seismic surveys. So there's been a lot of that information gathered to date, but presumably in the future, there'll be additional 2D, 3D programs that will take place on cable routes, for example. Again, all with the idea of trying to identify locations of hazards and avoid them if at all possible. On the far right side, you can see an image of a tool that's used to actually remove boulders that could be in the way if avoidance is not possible. And with the ultimate objective here, you can see this image is of the Demi Orion, which is an installation vessel. It's been in Halifax and Sydney many times over the last couple of years. And in the middle, you can see that sort of large cylindrical white structure in the middle of the vessel. That is a monopile being installed, and so we want to avoid hazards if at all possible before installing these structures, and so avoiding boulders, avoiding unstable seabeds and things like that will ensure success in the future. So Waleed, with that, I'm going to end this section and pass it over to you.
All right, thank you. I hope you can see my screen. Blair, can you give me a sign if you can see my screen?
Yep, all good.
All right, perfect. Yeah, so thanks, Blair, for the nice first part of this webinar. And Claire, thank you also for the organization as well as for the introduction. I would like to, before I start with my subject, I'd like to also show a couple of slides about who are we at JBO and what we do. And I need now to switch screens. So, all right. So for us, JBO, we are a consultancy. We're a designer for offshore wind. We've been working in offshore wind since 2008. Here we have just two diagrams to show our track record. We have roughly 40 gigawatt of installed capacity where we did play a role. So either it's on the left-hand side, you see what type of foundation it was, whether it's a monopile, jacket, gravity base, tripile, tripod, or floating. And on the right-hand side is to which detail level did we work into that particular project or that particular number of megawatts. And we do have, if you look at the detail design, we are a little bit higher than 20 gigawatt, where we developed basically the detail design for the substructures. And our services, we start from a very early project phase, from all the way into the initiation, all the way to operation and grid connection. We support in the 3D ground modeling, due diligence, environmental impact studies. Moving forward through the developing, we do the site condition assessment, the geotechnical survey, and the seismic analysis. In the engineering, we do the design for the foundation as single location design. We consider the ice loads, wave loading, wind loading, seismic analysis, cyclic degradation, etc. We support in the construction also with dynamic pile testing, as well as driving fatigue assessment and installation support. And during the operation, we also support in the periodic inspection, lifetime extension, BIM, asset value, etc. Here, just to show a couple of our track records. So we started back in 2006 with the Arkona Metmass in Germany. 2008 was the very first offshore wind farm in Germany, Alpha Ventos, where we designed the tribots. All the way to recent years, where projects such as Baltic Power, which was recently installed in Poland, North Cluster, which was installed in Germany, and the majority, of course, of the substructure we had were monopiles. There's a good reason for that. I'll show it in the next slides. Now, I'm going to focus mainly on how we choose the type of substructure we would like to use and why some projects go for monopile, single piece monopile, or a monopile with a transition piece, or why do we go to jackets or gravity base. So this is the situation globally up to 2024. So up to 2024, we have roughly 440 offshore wind farms. We're talking about almost 15,000 wind turbines installed offshore. From those, a higher number than 8,500 is installed on monopiles. So we can see that the monopile is dominating the market. There's a good reason for that. It's very simple to install. It's very cheap to fabricate compared to the others, especially jacket structures. And it's bankable. Bankable, it means because there's a lot of track record with monopiles. That's why it's much easier to get financing if you want to move forward with a monopile. And if we look, again, globally speaking, in the next 5 years, we can see that we will add roughly 10,000 wind turbines if all the plans go through and FID is achieved. Also from those, we anticipate that a higher number than 8,000 of those wind turbines will be also installed on monopiles. And as you can see, we keep pushing the limits with monopile. When I started, it was till 20 meters, then moved to 25, then XXL monopiles that went up to 30-meter water depth. And now we're even discussing installing monopiles to water depths of 50 plus meters all the way to 60 meters. Yeah, and here I just wanted to show you how the weight and the dimensions of the monopiles basically grew every year. So when we go back to 2014, where the turbine classes were still at around 5 megawatt, we had monopiles that used to be 650 tons. And at that time, they were considered to be heavy and large. And we were actually calling them XXL monopiles. But if we move now, we can see monopiles in some projects reaching up to 2,000 metric tons, with a diameter of 9 meters and 11 meters in some cases. Of course, the turbine class changed from 5 megawatt all the way to 15 megawatt. We're now building in more challenging environments with, if we go to APAC, it's typhoons, hurricanes, ice loads, and higher water depths, of course. But we can see the industry in general, it keeps pushing the monopiles as long as it's possible. And in specific cases, they'll switch to a jacket or gravity base, as long as we're talking, of course, bottom fix and not floating. From JBO perspective, we did a lot of analysis to say, or to see, or to tell our clients, where are we heading in the future? And we see that we will reach a maximum diameter for the monopiles of up to 12.5 meters. Till 2030, 2035. So the next projects we see will be below this limit, but we also see the monopiles will reach 120-meter length, and in some specific cases a little bit higher. And we can see the weight go as high as 3,000 tons. And the new installation vessels, or a lot of installation vessels that are currently available on the market, they can handle those weights and those dimensions, but of course, it will come with a price. Now, here, I wanted to show what is with the supply chain. Of course, if everybody is trying to build offshore wind, everybody is trying to build monopiles. How does the supply chain that we currently have, of course, will work or will be sufficient? And here I have 2 diagrams. I would like to take your attention first on the first one. Here, basically, we see the different projects divided into 3 different levels. High confident, those are projects that already achieved their FID. Medium is project that we believe will be built, but they still haven't achieved it yet. And low is projects that were announced, but there's still low confidence that those projects will be built or will be achieved. And the yellow line, this is the capacity for monopiles from the European fabricators. And as we can see, the European fabricators that we have at the moment for monopiles, in a lot of the cases, will be able to deliver the demand for monopiles fabrication in a couple of years, not where we have some impasses. But this is where the second diagram come in play. And in the second diagram, basically, this is just focused on the fabricators in the APAC region, especially China, where we can see their demand, local demand of the projects, and we can see, again, with the yellow line, what is the capacity that they can achieve. And basically, the red part of those diagrams is the number of monopiles that they can basically export to other markets. So from supply chain perspective, globally speaking, there is enough supply chain to deliver those monopiles. Now, to go specifically on the design and what affects the design and the foundation also choice. Basically, here is the slide that summarizes it all. So when we look at the turbine itself, not only the foundation, so we're looking at the turbine, the tower, and the foundation. The turbine itself is a serial production. And as Blair mentioned in his slides, we do have different certification levels, type I or 1A, etc. And the choice of turbine depends always on the winds, the average wind speed, and the turbulence intensity. And looking at the numbers, Blair, that you showed, I would say the turbulence intensity in Canada would also be higher than the US, my assumption. And that's why we would need to go to 1A. Yeah, so basically the turbine itself, the blades, those are typically serial production. So that means Vestas, Siemens, Mingyang, GE, they try to design it once, sell it for all the wind parks, get their type certificate. But the tower and the foundation usually are customized per project. What we see also happening is that the tower is usually 1 or 2 per project. So it's 1 design, 2 designs per project. But the foundation, which is in this case, I drew a monopile, it's location specific. So every location has a different monopile because it has a different embedment length or a different water depth. And when we look at the effects on such a substructure that contributes to the choice of the substructure design, we have the wind loads, the turbulences, the wave loads, the current, the water depth will play a role. The turbine size, of course, will play a role, as well as the geotechnic and the soil type and the pile soil interaction. So basically taking all those loads into effect, we have to consider, as doing the design in pre-feed or in feed stage, to determine what is the best foundation type for this particular location. And again, looking at the soil data that were previously shown in Blair's slides, I would say monopiles look feasible for the sites. Of course, with the higher loads, that means those monopiles most probably will also be heavy, but it's something that the supply chain can account for. But there are typically other elements that are involved in choosing the substructure design, not only the loads perspective. We also have to look at other items, such as environmental requirement, risk mitigation, the supply chain itself, boards, if they're available or not, if there's any particular emphasis on local content, and for example, we need to shift the design in a certain perspective to support local industries, as well as regulation. To give you an example, within the German waters, gravity-based foundations, because they cover a large area of the seabed, that is considered to be not environmental friendly. And this is a reason, for example, why even though gravity-based foundation would be sufficient in a lot of the sites in Germany, but that is the reason where the government or the regulators will say, please move away from gravity-based to monopiles or to jackets because we don't want to cover a huge area of the seabed because we consider this to be pollution. a regulation like this can exist anywhere around the world, and those regulation might and will affect the choice of the foundation type. Now, when we look at the current standards, and in this case, again, looking specifically at the monopiles being the dominant substructure type, and what we see is that the WG suppliers, basically the tower suppliers, they strive to standardize their tower in sections, in length, in the outfitting, and even in wall thicknesses. So they try to keep basically the tower standards because this is the business case. This is the easy way forward also to achieve the supply chain and to be able to deliver turbines for multiple projects. For the monopiles, what we thrive as engineers is to get location-specific design. That means every monopile is suitable for a certain specific location. It has a unique embedment length. It has a unique wall thickness, etc., to optimize the LCOE as well as the CapEx investment on the foundation type. We do have a clear responsibility split, which is around the interface level between substructure and tower. And what we notice is that the towers are typically optimized to a much higher level than the foundation. So for example, the WG supplier, they have their own SN curves, they have their own attachment geometries, and we can see that the level optimization on the towers is higher than what we can do with the foundation. I don't have the real numbers, but for example, the SN curve for welded connection as welded for one of the WG supplier is better than the SN curve for best material that we use as foundation design because they have their testing, they have their own fabrication yards, and they can basically achieve all of those standardization that are required to be able to use those higher SN curves. Now, when we look at the foundation and the substructure design, so basically this is a play between different disciplines. So we have the geotechnical designers and experts. They need to work together with the load simulation team and the dynamic team, together with the structural designers, as well as we have to consider the installation philosophy and method during the design. So by considering those four aspects, we have to loop the design multiple times in order to optimize it. So that means we design the support structure, we look at the pile-sol interaction, we model the turbine and the support structure together, we do the integrated load analysis for the entire system, with regarding to wind and wave, and in some cases seismic. We do the natural frequency check. We design again for ultimate limit state, fatigue limit state, serviceability, and accidental load cases. We optimize the design one more time, and we basically need to loop this multiple times until we achieve what we believe is the optimum design. And Blair, before I move further to specifically in Nova Scotia, I can basically give you the screen again to continue.
Okay, thanks, Walid. Can you see my screen okay?
Yep, looks great.
All good? Okay. All right, so I'm going to speak a little bit about grid integration, cable routing, and landfall considerations. So this map should be familiar to most everybody. It outlines the designated wind energy areas. And you can see also some prospective landfall locations for an export cable. So starting on the Cape Breton, the northernmost location, you see a yellow triangle, and then moving farther to the south and to the west, you can see a number of other triangles that would either coincide with existence of current infrastructure, or just the closest location to the offshore wind farm location of the future. The point being is that these locations probably are being discussed internally, but it will be important to get these locations disclosed, let's say publicly, to hopefully speed up the eventual approval process for sites and determining how the cost of these landfall locations are going to be borne by either the developers or cost shared with government, for example. But these locations should, again, I believe are being discussed privately, but at some appropriate time in the future, should start to be out into the public domain for buy-in. So a little bit of discussion about there's in general two different ways for a cable to make landfall. One being buried or HDD. So the term HDD meaning horizontal directional drilled. So basically a conduit or a borehole that's drilled on the land side underneath the beach area, rubble zone, what have you, and then poking up in the water through the seabed some distance from shore. Very common, well-developed method of doing a cable landfall. Also, the cables can simply come on the surface. So there's pros and cons to both approaches. I will say the HDD approach, it's been used actually in Atlantic Canada. So the Maritime Link, for example, the Strait of Belle Isle crossing in Newfoundland, Labrador, those have all employed HDD techniques to make landfall. And then also most, if not all, of the current New England offshore wind projects are also using HDD or horizontal directional drilled methods to make landfall. So for our region in particular, just some pros and cons considerations. Certainly not making a pick here, but things that will be contemplated by developers and government and regulatory agencies, I'm sure, would be if I talk about the French Bank, for example, the Eastern Shore region of Nova Scotia, possibly near the Halifax region. It's the closest point to this offshore wind farm of the future, the French Bank. It's got proximity to existing grid infrastructure and port infrastructure, which is important. Carries risks, everything does. Strong community environmental sensitivity near Halifax. So, it comes to stakeholder engagement, consultation, and trying to find a middle ground and compromise solution. Let's say if in fact the French Bank makes landfall in the future. Similarly, for the Sable Island and Middle Bank location, again, the Eastern Shore region being attractive, the Sheet Harbor area or Musquodoboit Harbor region, Guysborough County also, which is, location-wise closest to the Sable Island Bank. It's got a lower population density versus Halifax, and it has existing industrial and marine activity in that region. Again, risks, fishing activity in the region, shared use of the sea is important, and limited grid infrastructure in that region compared perhaps to other parts of the province. The Sydney Bight location, just to the northeast of Cape Breton Island, landfall locations near Sydney and industrial Cape Breton. You've got Glace Bay, the New Waterford corridor. So you've got existing Nova Scotia power generation plants there with existing infrastructure, being the Lingan and the Point of Coney site. Again, for existing infrastructure, you've got a well-established port of Sydney. You've got transmission infrastructure. You've got industrial land. You actually have, because of the maritime link, you've got subsea cable landfall in and around the Port of Coney area. A cable that has come across from Newfoundland, so that's already in place since I think 2017 or 2018. But again, risks and probably the risks would be the same for all these locations. But fishing activity in the region, public consultation and buy-in, stakeholder engagement. So a few considerations again with respect to grid interconnection. There's similar seabed constraints that you've got both offshore OSS, meaning offshore substations to consider, as well as land-based substations. So for an offshore substation, you've got seabed conditions, avoidance of boulders and unstable sands or seabed conditions, which I talked about a few moments ago. Offshore wind farms typically use HVAC or HVDC for export, depending on a number of factors, distance probably being the main one. So analyzing cable routing, landings and substations and converter stations, all this work is probably taking place to a certain degree right now. But at some point in time, this is going to have to kind of go out into the public, let's say. Proximity to high voltage transmission lines or onshore consumers is desirable for a landing location. So, this Nova Scotia Power Map shows existing infrastructure in certain areas. If you see the Canso region of Nova Scotia with existing infrastructure. Obviously, the Halifax, Dartmouth area has existing infrastructure from a Nova Scotia Power perspective. Fairly limited infrastructure in between. And then finally, as I mentioned earlier, if you look at the Sydney Bight location, 2 coal-fired power generation plants, but a lot of existing infrastructure there that may be repurposed in the future. So this is a location, a map that shows the 2 decommissioned pipelines from Deep Panuck and the Sable Offshore Energy Project. So probably no surprise to the audience that these pipeline routes are fairly well understood in terms of data collection. There's an actual installation campaign that's taken place a number of years ago to put the pipelines in place. So the data is there, and that would help to de-risk this route for possible future export cable corridor. And possibly this would allow some type of pre-approval, let's say, of an export cable corridor. Pre-approval meaning helping to consult with prospective developers and form some type of a consensus on a export cable corridor if this is, this route may be acceptable to prospective developers. It may not be. But if it is, then, groundwork should begin, if it hasn't already, on, the potential to have this pre-approved to lessen the regulatory burden ahead of time or take it off the critical path, so to speak. Once hopefully leases are sold to future developers, taking this burden, let's say, off of their plate, so to speak, may be helpful. Obviously, this location is not of use for the Sydney Bight, but I think you get the idea. So this is a kind of I find a helpful cartoon. It's an actual cartoon of the offshore Sable pipeline. You can see on the far left, that's the offshore location where the T-boat platform used to be. It was removed a number of years ago, decommissioned, and you can see how the pipeline in the past was buried and trenched, and some of it, when you move into the more of the middle and where the water starts to get deeper, it was sort of more or less placed on the seabed as opposed to being trenched. Water depth varies from 20, 30 meters on the left-hand side, and going to a bit of a trench down to 130 meters of water depth and then eventual landfall. So the point being here is that it's not just a flat seabed out there. There's lots of features that have to be understood wherever an export cable may be placed in the future. And for this particular location, there is a considerable amount of information that is already in existence and gathered. A little bit on subsea HVDC concepts and actual projects in place. So on the left-hand side, you can see the Maritime Link. For those of you not aware, it's a HVDC cable from Newfoundland, Labrador to Cape Breton Island. That is the red line on that schematic. It's been in operation since late 2017. So good news is that there's a lot of technical know-how that came from that. There's cost information, although it was almost 10 years ago, but cost information that has come from that. And that will help inform future decisions if subsea cable ever becomes a reality. Not saying it will, but if it does, the data from an actual project in Atlantic Canada is going to be helpful. On the right-hand side, you see a concept that's been put out in the public of a potential subsea cable from Nova Scotia to New England. Again, that's something that is going to be considered and cost benefit amongst other options that could be out there. A little bit more on the Maritime and Atlantic Link. So the Atlantic Link was actually proposed as a subsea HVDC cable from New Brunswick to Massachusetts. It was proposed by a mayor, I believe, and it was approximately 375 miles, 600-kilometer pipe HVDC cable with costing that was proposed. This was part of a public tender that the state of Massachusetts put forward, and eventually an overland route was chosen instead of the subsea cable option. But that's not to say that subsea cable options may not be the most cost-effective or desirable approach in the future. I said at the beginning I was going to say a lot about Wind West, but here's a little bit. This is public domain information. For Wind West, you'll see cartoons or schematics out there of possible subsea cable route to Quebec. It's on the right-hand side, but also consider an overland route on the left-hand side. So that's all I'll say about that. For a possible offshore wind farm, we've run some numbers, conceptual design. In this case, a 700 megawatt wind farm, approximately 47 wind turbines on the Sable Island Bank. We chose that location for no specific reason, not to favor one location over another, but it was simply just to draw, put a concept on the board. We examined this location, as I said earlier, geotechnically suitable for monopiles, looking in conjunction with our colleagues at JBO. We looked at things such as an installation campaign. Could it be done in a single season, or would it take 2 or more seasons to install that many monopiles and wind turbines? It's possible. A lot of things would have to go right to do it in a single season, which is really good from a cost perspective. But if you see installation seasons spilling over into, more than one. That impacts cost, that impacts LCOE, as I mentioned earlier in the presentation. I'm going to try and speed up so that we try and stay under time. Again, substations will be required in the future, offshore and onshore. And I'll skip over that. And I think now we're going to be at our wrap up and conclusion. So, Wally, do you have anything in particular you wanted to show, or I can move to sort of the wrap up risk slide?
I have a couple of slides, which is particular about Nova Scotia and foundation design, but I'll also need to speed up with them, and then we go to the wrap up and conclusion.
Okay, I'll pass it over to you.
All right, thank you. So, it's working fine. So I'm on the right slide here. All right. So now focusing especially on Nova Scotia, and of course we have some challenges, but to every challenge there's a solution. So for example, do we need to import the monopiles in? We do have harbor infrastructure, as Blair mentioned, even some monopiles that were intended for the US, where basically the marshalling harbor was within Canada. The same thing for transport and installation. Installation vessels are available also for large monopiles, and they can be utilized. If there is no local large-scale fabricator, we can, even with that case, we can modify in the foundation design. This is something, for example, we did in a project back in APAC where there was so there were local content requirements, but there were no fabricator locally that was able to, let's say, build the monopiles. So the monopile sections were designed or built in Europe, welded in parts, but basically 2 or 3 welds were made in the APAC region just to satisfy the local requirement. Or there's a split where we say, let's say the foundation or the substructure itself come from one part and the secondary steel come locally. If it's high capex, then the solution would be to develop an efficient foundation design, long lead for final assembly. The time critical elements have to be designed or ordered in an early stage. And of course, there's a high wave and wind loads, as mentioned by Blair previously, but the foundation design have to be basically designed to withstand those conditions, and design optimization has to be considered in order to lower the LCOE. Now, just to give you a general understanding about the cost between the single piece foundation, or so basically it's a monopile, but I have 2 different types of those. One, we call it the P-less design or a single piece. The other one is your typical monopile transition piece monopile. And the third one is the jacket foundation. Of course, there's other foundation types, 3-pile, 3-pod, gravity base, but I chose those because those are the basically dominant ones that are used in the industry. So the fabricating for the monopiles is semi-automated, where for the jacket, there's a lot of manual welding involved. At the moment, monopiles can reach up to 60-meter. Jacket, we can say they can go up to 75 and even a little bit higher, but the cost will increase, of course, with that. When we look at local fabrication at the moment, considering what is available in Canada and Nova Scotia, I would say for the monopiles, maybe we can consider secondary steel there, where the monopiles and the automation has to come from somewhere else. For the jacket, I did the same thing, even though I know there are some jacket fabricators over there. The reason I did it this way is because a serial production jacket is different than a single piece jacket foundation. For the weight dimensions, the monopile is high, the jacket is lower, the lead time is the opposite, and capex and opex, as you can see below. Of course, we're pushing the limit when it comes to wind, wave, water depth, and we say monopiles go up to 60, but what happens if you go to 75 meter or 80 meters? If we switch directly from a monopile to a jacket, it will be very expensive. We at GBO, we developed some kind of what we like to call a hybrid foundation that you can see here in this schematic cartoon, I'm going to say. So basically, this combines both worlds. So we have a small jacket in order to make sure that we don't have a very heavy foundation, and also to transfer the loads on multiple piles to the ground. But instead of having the transition piece for a jacket, which is typically above water, we can push that thing underwater, calculated with CFD, and also we can do the design and the corrosion protection for it. And basically extend the TB, or what we like to call a monopile, a little bit. With this kind of concept, it's even though it's heavier than a jacket, however, it's cheaper because again, the monopile part is semi-automated fabrication. Uh, Also, installation vessels will not have a problem with the boom length or the boom height. We did it for a project between 75 and 85 meter water depth, and we were able to do a design, push it also through early certification, and it went through. If you have a difficult soil condition where a monopile, let's say, is not drivable or the soil is weaker than usually, basically it can be used as well. And because you can split it anywhere, like as a typical monopile transition piece, so even if the weight increased a certain level that a vessel cannot lift it, you can just split it and you just have a typical two installation campaign where you install the lower part and then the upper part. I'm not going to lose a lot of time about what is the aim of governments, basically, when they do their own permitting process. So looking at the German example, what the German government was interested in was the level of safety, the security of energy, and the level of pollution. Level of safety, the reason behind that is that because when we build offshore, we use a lot of guidelines that are basically maybe not the national guidelines. So for example, in Europe, we have Eurocode, which we use in Germany, but when we build offshore, we use a lot of, at that time, GL, DNV guidelines, or even NORSOC. They don't typically match from a safety level perspective. So from the German perspective or the German government in the permitting process, they really wanted to show that the level of safety is kept. Security of energy, again, from a German perspective, one more time, because Germany decided to switch off their nuclear plants. That's why they need to make sure that those offshore wind assets are robust and will stay, and they will not just fail and all of a sudden all the energy that they are dependent on is gone. And of course, we look at the level of pollution. We have to keep it under a certain limit. We have to make sure that the environmental impact is as low as possible. So when we look in the different stages here, sorry, I went too fast. For the first stage, we look at the design basis, the plausibility for the chosen foundation concept. We look at the environmental impact, and we also look at the completeness of the soil data. In the second step, we look at the soil investigation and the soil report. We look at, again, at the foundation design, this time on a detailed design level. And we also look at the type certificate of the wind turbine. And the final stage before we allow for installation, we look at the plausibility for the installation method as well as the transportation method. We also look at the noise impact, etc., during those processes. What we did, or JBO's experience in this regard, we are co-authors of the PSH regulations in Germany. We also co-authored the DIN 18088. This is a guideline that basically bridges the gaps between the Eurocode, which we use on mainland, to what we use offshore, where there are also some holes. We supported the BOEM in the USA also when they wrote their regulations when it came to noise, load assessment, typhoon loads, etc. And we also supported the BSMI in Taiwan for their standards for offshore WG and OSS based on the German experience in that time. Again, those standards are typically there to make sure that what is important for the government is also reflected in the design process and the installation process. So again, from the German perspective, it was environment, safety level, security of energy. In other countries, it can change and depend on what is important for that specific location. Blair, I'm done. So I can give it again to your slides.
All right. See my screen okay?
Yep.
All right. So this wraps up our presentation, trying to bring it to a point where we, basically identified sort of key risk categories throughout this presentation that we touched upon. And again, for context, to try and help the audience to see what the comparison is versus already established projects or regions. So in this case, the northeastern US and the North Sea. So in the case of the North Sea, a very mature, well-established industrialized utility model. In the case of the northeastern US, state Massachusetts, Rhode Island, New York, what have you, it's an emerging market, but they have projects under their belt despite the problems that has been encountered with the current administration. And it's a regulated domestic power model where, the market is there essentially where these projects are located, and sort of export over large distances, let's say, is not a thing. And then finally, so for Nova Scotia, we would call this, an emerging market, immature market. There's not a track record in offshore wind. So for that reason, a lot of these risks are by nature going to be high because, there's not a lot of information, or there's a lot of uncertainty. But anyways, let me run through these real quick, and then we'll try and hopefully get to some Q&A. So for the risk category of installation, the risk for Nova Scotia would be high, driven by a lot of the wind and wave conditions, icing conditions that we explained earlier. The potential for shorter installation seasons, a few months versus possibly year-round in other parts of the world. For fatigue loads, so again, driven by wind and wave, the dynamic environment that we live in, the risk in Nova Scotia would be high compared to other jurisdictions, requiring more robust and more expensive infrastructure, monopiles, jackets, nacelles, and wind turbines that are designed for icing conditions, for example, whereas in other parts of the world, that may not be the case. O&M, meaning operations and maintenance. So after a field is in production and operating, again, due to the environment in which we live in, being able to go and repair a wind turbine in the middle of winter may not be feasible. So that impacts downtime. It results in more downtime, which makes the overall project less efficient compared to other parts of the world. Regulatory risk. For our region, there's not been an offshore wind project to this point. However, we do have the benefit of an experienced regime in the oil and gas sector. So a lot of that know-how and knowledge is being transferred, as we speak, has been transferred into the bodies that are looking after offshore wind. Political risk. So in Canada, you're seeing a move, for example, to the Major Projects Office, for example. So that didn't exist a year or more ago. So you can see that, politically, there's a movement to help move large energy projects forward, and not tie them up, sort of in low value processes. But anyways, medium risk in that category. The market risk for us is quite high, but just simply because of the lack of demand here locally and the need to export power to make these projects viable or turn them into molecules. Cold climate and icing, high risk in our region compared to others. Shared use of the seas, again, mostly because we don't have a track record yet in offshore wind, but shared use of the seas with fishers, for example, that would be a high risk because it's simply an unknown or a lot of uncertainty in that area right now. That these items are being looked at now. We don't have the benefit of projects in the past that would be able to inform our know-how of shared use of the seas. Supply chain manufacturing. So if an offshore wind project were to begin today in Nova Scotia or Canada, all, for the most part, of the major components would come from Europe or Asia. That's just a fact. That's where the manufacturing fabrication capability is. From the supply chain services side, lower risk. driven mostly by the offshore oil and gas service and supply sector that we have. We have a very strong marine economy in our region that can lend itself well to the services sector of the supply chain. Indigenous consultation, high risk, duty to consult on the part of the developer and accommodate. Again, a lot of uncertainty here. We've not done an offshore wind project yet. Because of that uncertainty, that risk is high. And then finally, labor agreements. Medium risk, we have a track record of large capital projects, energy projects, mostly between Newfoundland, Labrador, and also Nova Scotia, perhaps to a lesser degree. But look at Muskrat Falls, look at the offshore projects off of Newfoundland, previously the Sable and Deep Chinook projects off of Nova Scotia. A medium risk category given there. And then finally, landfall and export cable. These locations should be defined, and consultation and sort of, let's say, pre-approval, if possible, of these locations and export cable routes. If that could happen sort of in parallel to the lease sale and work that developers will do in the future, I think that would be a good thing. So that's it. I'll pass it over to you, Claire, to sort of manage the Q&A.
Yeah, sure. Just because we're 15 minutes over, I might suggest that I will save all the questions out of the Q&A chat, and then we can follow up with written answers in the recording to all the folks that attended and registered to the webinar. But unfortunately, yeah, we're just kind of out of time, but great presentation, very in-depth. Waleed and Blair, that was a great overview as well to put Canada into context, looking at what has happened here in the past and internationally. And thank you both for taking the time to be with us today. With that, I am going to end us off here, but thank you all so much for taking the time this afternoon or this morning to join us, and we'll chat soon. See you in the next one.
Thanks,
Thank you.
Claire. Thanks, everybody.
Thank you.
Thanks, Waleed.
Bye.
Take care. Bye.
Bye-bye.